Okay.
Particle A have x1 and x1 dash. Particle B has x2 and x2 dash. Okay. So particle A will have the ellipse in whose major axis in first quadrant. Okay. And particle B has a ellipse whose major axis in second quadrant. Is that possible?
It is also possible in certain cases if you have wrong momentum of your particles. Wrong momentum means, suppose we are designing a machine for, say, let us say 1 GeV electron machine, okay? And your particle has certain energy deviation from 1 GeV. Means it can have 1.001 GeV or it can have 0.999 GeV. Means certain deviation from the correct energy, okay? If particle has exactly correct energy, the ellipse center is coincide with the orbit. X is equal to 0, x prime is equal to 0. But now, if energy deviation is there, and in optics, there is non-zero dispersion. There is dispersion. One term I have introduced you in lectures, that is dispersion. So if dispersion is non-zero, then your ellipse may be shifted, means ellipse center may be shifted. If energy deviation is much higher or dispersion is much higher, your center will be shifted so much that your complete ellipse will be in first quadrant if your delta P by P is positive or dispersion is positive further. In other case, means if your delta P by P is negative and dispersion is positive, then it will be shifted towards the second or third quadrant. Okay.
Okay,
But if you have any dispersion in point where you are looking or observing your ellipse, or your particle doesn't have any energy deviation, then this shifting is not possible.
So instead of shifting,
considering only ideal machines, if errors are there, means machine has certain errors. If suppose your magnet is not exactly what you want, this is always the practical case. Machine is not ideal. In that case also your center may be shifted from the coordinate origin of the coordinate system.
Okay, sir, let's not consider the origin in this case. So in the twist parameters, alpha corresponding to the whether the beam is diverging or converging, right?
Yes.
So what I'm just asking is it possible whether a set of particle have a positive alpha and another set of particle will have a negative value of alpha in the same beam itself?
No. Actually, alpha, beta, gamma is decided by the optics, not by the beam. Actually, beam has parameter emittance and optics has the parameter alpha, beta, gamma. Without considering any beam, you can define alpha, beta, gamma only by looking your optics arrangement. So optics arrangement, how you are arranging your magnets, quadrupole, drift, magnet, dipole, etc. It gives you the alpha, beta, gamma. Okay. In ring, actually, we choose the periodic solution. So that is the unique in case of ring. In transport line, definitely what you are choosing initial alpha, beta, gamma, that decides the alpha, beta, gamma downstream. Okay. So alpha, beta, gamma is decided by the optics only without considering the beam. Beam has emittance with it, and then these parameters alpha, beta, gamma combined with the emittance, then it will give you the beam size, divergence, etc. So at a certain location, you cannot have two different twist parameters.
Okay, sir, but while introducing the this parameters, while introducing the beta parameter, the lecture says the beta is the length of the optics where the betatron advanced to unitary. So, is that betatron didn't indicate the particles or particle oscillation on the time the particle doesn't matter there?
Actually, particles oscillations means displacement of particle betatron, means betatron oscillations displacement is indicated by the beta, means square root of beta is proportional to the displacement of particle at a certain location due to their betatron oscillations. If you want to know completely the displacement, then you have to bring the emittance also. Under root emittance beta, it gives you the with phase advance definitely under root emittance beta cos phi. This gives you the displacement of any particle from design axis due to their betatron oscillation. So beta indicates the displacement. It is not complete information, means you cannot have complete information without knowing emittance about the displacement.
Okay, sir.
I would also like to just add, in the beginning you said that emittance is representing a single particle. Actually, emittance or which is the area roughly proportional to the area of the ellipse represents millions of particles. So it's not a single particle, it's a bunch of particles. So emittance we always call it beam emittance. And beam consists of very large number of particles. It could be infinity, it could be very large. So larger the number of particles, more accurate will be the emittance. So
that's why distribution comes into the picture.
Distribution comes into picture, yes. So actually the boundary of this ellipse, which is representing the emittance, tells that the particle which has the maximum x and x prime or whatever parameters are involved in it. So it's not a single particle, it's a bunch of particles which are representing the emittance and which is representing the beam, not the single particle. This is just I wanted to make add to that.
In case of single particle, you can always tell invariant of motion rather than emittance.
Correct, exactly.
Sir,
Yeah, about to say that the outermost particles thing. So instead of that, I said particle. That's it.
Yeah, no, yeah. So it's the outermost particle which has maximum x and x prime. So that will represent the boundary of the ellipse. Otherwise, the area actually emittance is area of the ellipse. And area means the everything, whatever part, all the particles are within that ellipse. So it's not a single particle, it could be millions of particles. It's a beam actually. And beam may suppose, depending upon what is the current, beam will have very large number of particles.
And Dhanush also, as sir is saying that you can also estimate emittance statistically. Means what is the second moment of your x and x prime distributions of the particles. Billions of particles are distribution in the x as well as in x prime. So you calculate the second moment, that is the statistical value of the emittance. We generally quote as RMS emittance.
Yes, sir.
So, sir, how do we determine the emittance of the beam? Like, I have heard there is a emittance scan that is
yes,
done.
emittance can be measured using 2 or 3 different methods. Okay. So very simple method is paper pot method. paper pot method, what is this method? Actually, we have certain screen in which certain holes are there. Okay, means grid of holes. Now beam is passing through that grid of holes. So every hole, we know what is the x and y of that hole.
Okay.
And after some distance, we put a screen on which beam is producing some fluorescence or some electrical signals which we can record it. Okay.
So it will have some image.
Okay.
It will have some image.
But that will distort the beam, right?
That is destructive method, definitely destructive method. Okay, so this is one of the methods. There are 2 or 3 more methods. Even using synchrotron radiation, you can measure the emittance. Means in case of electron machines, electrons, when it revolves in the storage ring, it emits synchrotron radiation. So by scanning the synchrotron radiation, you can estimate what is the emittance of the electron beam which is rotating inside this storage. So paper pot method is a very simple method, and it visualize what is the emittance. That's why I am actually telling this method.
You can just estimate that.
Yes. So by distance between the paper pot and the screen, you can estimate the angles x prime and x and y, you know, by your grid. So you have information of x as well as x prime, etc. Then you can construct the complete distribution and emittance.
Yeah.
And slightly better method is scanning method. So you scan the profile of the beam, and that gives you the distribution of the particles in the beam.
Yeah, that is what is called the emittance scan, right? But
yes,
how it is
emittance.
different from the Vandermeer scan? Like in Vandermeer also.
Actually, that paper method is when the current is very small. So as you rightly said that it may distort the things. So when the current is very small, there will not be any diffusion, and you can get reasonably good emittance. But if the current is large, let's say several hundred microampere or milliampere current, then that method is not very accurate, and then you have to use this scanning method.
Okay.
But there are other methods are even better than that, because the scanning method again, because you are scanning on a wire scan method is called, and when the beam is falling on the wire, when you are scanning, there will be emittance of electrons. So the beam current will be slightly unrealistic, because from the wire there will be emittance of electrons. So it will not give you the exact reading of the current.
And emittance scan, as sir has said, that you have to scan the wire through the beam.
Correct.
Means as wire is passing through the beam, it secondary electrons are generated in the wire, and you collect the information through that. And Vandermeer scan is that you steer the beam itself. You steer the beam, you steer the bunch to overlap each other. So that is Vandermeer scan. Okay.
So basically, what is the scanning?
Scan means we are moving wire transversely through the beam. Means one wire is inserted in the chamber and we move transversely, means along X or along Y. And as it passes through the beam, the electrons which hits the wire, it generates secondary electrons. and those secondary electrons can be counted using the circuitry outside. So it gives indirect estimation of the current which is inside the beam. At different locations of X, you can get different currents. So you can construct complete profile of the beam using this scan.
And that is the case when the accelerator is electron accelerator. So suppose you have a proton accelerator or heavy ion accelerator, beam consists of protons or heavy ions.
So in that case, the wire will not work, or?
In that case, wire will work, but secondary emission will be very huge.
Oh, yeah.
So correlation will be a bit difficult than the electrons.
Now, I'm just thinking right now that if the electrons are coming out, see, the electron coming out depends on the energy. So more the protons, let's say, more electrons will come out, and it will be proportional to the number of protons. So if at the corner, if the number of protons are less, then less number of electrons will come out. So there will be a factor. If more protons, more electrons will come out, and at the end, when the number of protons are less, the number of electrons also will be less. But there will be a factor. There will be some factor. So your distribution will only shift. So by that factor, your emittance will change. But distribution may still remain same because it is shifted by the factor.
Yeah, right.
In negative ion cases, some problem may be there. Because the negative ion itself has certain electrons that can also contribute.
Yeah, that can also contribute. And in the MLA is slightly, because if it is light time, then the work function is less. Work function is more, in fact. And suppose it is very heavy ion, let's say cesium or something, then the electrons will come out very easily. So the large number of electrons will go out.
Yes, I have in my mind H negative ion, which is very loosely bound electron.
If you take cesium, then it is more loosely bound.
Yes, yes.
So all those factors have to be kept in mind.
So we should consider a wire which has a high work function.
Exactly. Normally, tantalum or titanium wire is used. Never use any copper wire or something like that.
Yeah, copper will be giving, too much noise, or
too much noise, and lot of electrons will come out.
yeah.
So I think titanium wire is mostly used.
Sir, you refer that the twist parameters are the function of optics, right?
Yes.
Then why can't we consider in such a way that the optics where the twist parameter alpha is always negative, so that it will converge the beam rather than diverging it?
Now suppose you have a synchrotron, means same point will be repeated again after one turn. So you have a closed form solution, means your Hill's equation should give a periodic solution to us. Okay. When you impose the periodicity condition on the Hill's equation, you can get a unique value of alpha, beta, gamma that is periodic itself. That's why we cannot consider alpha as other than this periodic values. Okay.
Okay, sir.
Because there is certain boundary conditions on Hill's equation, that is periodic boundary conditions. So you have to get the solution under that condition only. That's why you get this unique solution in that case. Definitely for the transport line, where initial parameters decide the alpha, beta, gamma. Initial parameters means, suppose transport line is just after the electron gun. Electron gun itself has solenoid for focusing, etc. So in that case, you have to consider what is the initial alpha, beta, gamma which you are obtaining through the gun, and then that will be propagated along the optics which you have arranged. So in that case, initial alpha, beta, gamma, if it is changed, then downstream all the alpha, beta, gamma in the transport line with the same optics will be changed. But that is not the case of the synchrotron, where we have periodic boundary conditions.
So according to a point, we don't need any type of focusing coils or else the quadrupole magnets for transferring lines. Is it so?
The transport line needs it. If suppose electron guns is sending some beam, how you will send it to say 50 meter or 20 meter distance where the accelerator is situated? You have to transport your beam from one place to other place, and it should be kept focused. So quadrupole, solenoid, dipole magnets, all are there in the transport line. Theory is same. I am only saying that in case of transport line, you have to solve Hill's equation under the initial conditions, means it is an initial value problem. And in synchrotron or storaging, you have to solve Hill's equation under the periodic boundary conditions. Means in one case you have boundary value problem, in one case you have initial value problem. Okay, so in case of initial value problem, you can have different solutions on the basis of initial conditions. In periodic boundary condition, a unique periodic solution can be obtained. That's the thing.
Okay, so now I can understand.
So, Pitambar sir wanted to show some slides. If you are ready, sir, you can show.
Just a minute, the last question I have.
Oh, okay, no problem.
Okay, so we are discussing about the simple periodic cell, right, in photocells.
Please say again.
We were discussing about simple periodic cells, photocell.
Yes. That is just an example of optics
yes,
calculation. Yes.
Yes, on the time in these things we are just discussing about the matrix of defocusing quadrupoles and matrix of drift space and these things. On these matrices we are just using the thin lens approximation, right? Then only it will simply form 1 by f like that.
Yes.
But even though we are using thin lens approximation, we are just considering from this off to that off. That means from this focusing from the midpoint of focusing quadrupole to that midpoint of focusing quadrupole, it's one period. How it is possible after considering the thin lens approximation?
And thin lens approximation means length of the quadrupole tends to be 0. Okay.
Is that exactly
so what will be the location of your quadrupole? So definitely location of the quadrupole will be in between some body of the quadrupole. Okay.
Sorry.
So where will you locate your quadrupole? Suppose quadrupole has some thickness and you want to represent it using thin lens. So where that thin plane will be kept?
Okay.
Where will be kept? I am just asking you. Where will be? Suppose
like-
some quadrupole has a 500 length and you want to represent it with the thin lens approximation. You means you will put a transverse plane in the place of 500 transverse plane of just length 0. Okay. Where will you put this transverse plane which will represent the
midpoint at the midpoint of 250?
Okay. So we are putting quadrupole plane at those locations. So drift space is from midpoint of the first quadrupole to midpoint of the second quadrupole. Okay.
Yes, sir, but is it still legible? Because even though we have a finite distance or finite length of quadrupoles, we are using thin lens approximation. Is it okay?
Okay. Under certain conditions, this thin lens approximation gives a very bad results. What are those conditions? Suppose your betatron wavelength means quadrupole is exciting some betatron oscillations. So if betatron wavelength is comparable to the length of the quadrupole, your results will be drastically wrong if you are using thin lens approximation. So thin lens approximation works where your quadrupole thickness is much smaller than your betatron wavelength. In that case, it is fairly correct results which you obtain using thin lens approximation.
Okay. So betatron frequency wavelength should be greater than
much greater than your thickness of the quadrupole.
Okay. Okay, sir. Thank you.
Okay, so if you have no more questions, I'll request Pitambar sir if he want to share the slides.
No, I'll actually, I wanted to improve that slide, but somehow not coming.
Oh, I mean, you want to present it, or you cannot find
No,
this?
I think I'll show it next week.
Okay, no problem. Then
because I wanted to have the comparison of two.
Okay.
So I wanted to make both of them. I have made one only.
Oh, okay.
But I wanted to make a slide with the old one also and tell what is the change which we have made. So I'll do that in the next week.
Okay. Okay, sir. No
Then
problem. Then Amlendu sir can start with the solution.
Okay, I am sharing this screen.
Okay.
Is it visible?
Yes, sir. We can see. You can go to full screen. Yeah. Now it's full screen.
So this week mainly Hill's equation and parameterization, chromaticity, etc. were covered. So there are certain problems in the assignment 10 which seems to be tougher. So I am covering the solutions of those which were asked in the forum also. Okay. So first is the problem 3. In problem 3, what we have a transformation from coordinates x prime to some other coordinates, say xn and xn prime. Y subscript n, it will be cleared after this solution. Converts ellipse into the circle. So if x, this new coordinate is x upon root beta, what will be the other coordinate in this coordinate system which will convert this ellipse into the circle? So let us start with this case. A circle can be represented by two coordinates as x is equal to a cos phi and y is equal to a sin phi. A should be the constant here and the same constant. A here in x also, a here in the y also, and this should be a constant, not the function of s. Then these two coordinates will represent simultaneously the circle. So how we will convert our ellipse into the circle? That is the question. So definitely we have to obtain some coordinate transformation which transforms our coordinates to such form in which amplitude really becomes constant. In our case, amplitude is actually under root emittance beta. Here beta is S dependent, means amplitude has S dependence. Amplitude is not a constant. That's why we don't get circle in our case. So we have to make certain coordinate transformation which makes this amplitude as independent. Means if this amplitude becomes constant, then we will can get the circle. So first transformation is very easy. You can see here, if this beta can be brought down here in the denominator with x, then we will have under root emittance cos phi, and under root emittance is a constant. So x can be converted very easily, which can be a candidate for representing a circle. Now if you can get x here, the other coordinate should be either under root emittance sin phi or minus under root emittance sin phi. Sign doesn't matter whether it is plus or minus. So you can get that if you differentiate this x with respect to phi, then you will get another coordinate yn minus under root emittance sin phi. Means dxn by d phi, n is subscript here, which is the new coordinate. You can say x new. So dx new by d phi will give you minus under root emittance sin phi. So now you can see our new x coordinate is under root emittance cos phi, and under our new y coordinate is under root emittance sin phi. So these two coordinates will make the circle. Now we will relate these new coordinates with the older one. So x already has been related. Now what is the y in algebraic form with x? So we have dxn by d phi. And in accelerator, we always have differentiation with respect to s. So dx nu by ds and ds by d phi. This expression can be written down as. Now dxn by ds, we can calculate this value using this relation. Xn is equal to x upon root beta. So we will get relation in y and x, and ds by d phi. This is definitely beta. This is the definition from the beta, in which d phi by ds is equal to 1 by beta. So just ds by d phi will give you the beta. So y new coordinate will be beta into dxn by ds. So now it is remaining to calculate only dxn by ds. So we calculate it. So dxn by ds, because you have x nu is equal to x upon root beta. Root beta is also a function of s. X is also a function of s. So both will be differentiated. So differentiation is straightforward. You will have minus x upon 2 beta root beta d beta by ds. This time I am differentiating beta, and now keep the beta aside and differentiate x. So 1 upon root beta dx by ds. Now you know that minus half d beta by ds is basically the alpha. We say that this parameter is alpha. So alpha upon beta is square root of beta x plus 1 upon root beta, and this dx by ds is basically x prime. So now you have dx and ds in terms of x and x prime. However, our new coordinate was beta multiplied by dx and by ds. So if we multiplied this value with beta, we will get the second coordinate also. So now first coordinate is x by root beta, and second coordinate is alpha upon root beta x plus beta root beta x prime. So these two new coordinates, which is transformed from x and x prime, will give you the circle in the phase space rather than ellipse. This is known as normalized coordinates. And this is not only the case of accelerators in which we use it. In nonlinear dynamics also we use normal form approach. And this is just the beginning of the normalization of the coordinate system, which give you the normal form. In normal form, nonlinear resonance can be studied very, very beautifully. So this is simple linear dynamics case in which ellipse is converted to circle. So these two coordinates are there. So just the answer should be this. Now problem 4. Problem 4 also has certain queries on the forum. So in an optical channel, the aperture means radius of the vacuum chamber in one plane is 12 mm. If in this plane, optics has beta function ranging from 2.5 meter to 9 meter, means we have certain vacuum chamber of the same radius throughout the synchrotron or say some accelerator, and beta on the periphery varies from 2.5 meter to 9 meter. What is the largest value of emittance so that particle pass through the channel without being scraped by the chamber? Now we have chamber radius 12 mm. So ideally the beam size can go up to 12 mm. Up to 12 mm, if beam goes, it will just pass through the chamber. It will not be scraped by the chamber in the ideal case. So we think of as under root emittance beta x should be 12 mm. So emittance max will be 12 by beta, and now beta is varying from 2.5 meter to 9 meter, means this value of emittance will vary 57.6 millimeter milliradian to 16 millimeter milliradian. Now at certain places where beta is low, 57.6 millimeter milliradian emittance can also pass. But where beta is high, only 16 millimeter milliradian can be passed. Means if we see in totality, 16 millimeter millirad is the limit on the emittance. If we have larger than this emittance, at certain locations it can be scrapped. So 16 millimeter millirad is the largest emittance which can be passed without being scrapped through this channel. This is sometimes known as acceptance of that channel. Okay, so the correct answer is 16 millimeter millirad, which is the option A.
Sir,
No problem. Yes.
Can you please repeat the last thing that you said? How you choose between 16 millimeter milliradian and 57?
Suppose you choose this 57.6 millimeter milliradian, but at certain point, say S is equal to S1 where beta is high, only 16 millimeter milliradian emittance can pass. So 57.6 millimeter milliradian emittance, when will we pass through that narrow point, it will be scrapped. Particles will be scrapped from this beam. So 16 millimeter millirad is the emittance which will be passed from everywhere without any problem. So 16 millimeter milliradian is the largest emittance which can be passed without being scrapped. Is it clear or not?
So if we have two values, we should always choose the lower one in the case of emitter.
Yes. Because bigger one will be scrapped at certain narrow point if you are where the beta is high.
No, sir. My basic question is whether the bigger one, the 57.6, is eliminated due to the size of aperture, or generally it's a greater value, so we are eliminating.
It is due to size of aperture. 12 mm is constant everywhere, but beta is varying. So where the beta is high, the limitation is coming from that point, no?
Oh, okay.
So we have to choose when beta is high. When beta is high, you can see the emit means in this equation. If you have lower beta, you will get higher emittance. If you will get higher beta, you will get lower emittance. But if you suppose get lower beta, you can get higher emittance. But when this emittance will pass through the point where beta is very high, there the limit is low, so outer particles will be scrapped. So if you want to save your particles, the minimum should be chosen. Okay. Is it clear or not?
Yes, sir. Yes, sir.
Now problem 7. At a location in a synchrotron, the value of beta function is 30 meter. A particle in a turn is just crossing the design trajectory at this location with an angle of 4 millirad. If betatron tune is 1.125, what will be the displacement of the particle from the design trajectory in the next turn at this location? Okay, now you can see that this is the problem of initial conditions. Means in the first turn, you have x as well as x prime. X is means it is just crossing the design trajectory at that location, means x is 0 because it is on the design trajectory. So x is 0 and x prime is 4 millirad. So you are given initial condition. You can say this is the 0th turn. X is equal to 0 mm and x prime is equal to 4 millirad. And after one turn, when it passes through this point again, what will be the x and x prime? This is asked. And you have given tune and beta function. So definitely these initial conditions which have been provided, we will use those conditions here. So deviation in the trajectory from the design path is x is equal to under root emittance beta sine phi. After one turn, because we are looking at the same location, so beta is same, emittance is also same, only phi changes. So how much change will be there in the phi? Say delta phi. So next turn x will be under root emittance beta sine phi plus delta phi. And this delta phi will depend on the tune, because tune is basically phase advance in one turn divided by 2 pi. So delta phi is basically 2 pi into tune. So we have written is phi plus 2 pi nu. This is under root emittance beta sine phi plus 2 pi nu. This is x after one turn. Now angle of the trajectory with respect to design path, if we have x is equal to under root emittance beta sin phi, if we differentiate it with respect to as dx by ds, we will get x prime. So let us differentiate it. So dx by ds, you have to differentiate it under root emittance. First differentiate this beta. So beta prime upon 2 root beta sin phi plus under root emittance beta, and now you differentiate this sin phi. So differentiation will be cos phi and then d phi by ds. d phi by ds will give you the 1 by beta. Now here you have under root beta and here beta. So there will be under root emittance by beta here. Now apply, we have x and x prime. Now apply initial condition which is provided in the problem. So first we apply here x is equal to 0. Now you know that emittance cannot be 0 and beta cannot be 0. So definitely sin phi is 0. So sin phi is 0. So we take very basic condition phi is equal to 0 as the initial condition. Now, if we will put phi is equal to 0 in this second equation, x prime, because x prime is given 4 millirad. So x prime is equal to this sin phi will become 0 and cos phi will become 1. So this will be under root emittance by beta. So under root emittance by beta is equal to 4 millirad. So under root emittance will be 4 millirad into under root beta. And beta is given as 30 meter. So 4 millirad into 30 meter. This is your emittance, under root emittance. So now you know under root emittance. Also, you know tune. So using this expression, you can calculate what will be the displacement of that particle after one complete turn. So this will be x is equal to under root emittance beta. Under root emittance is just 4 into 10 raised to minus 3 into root 30. Then there is under root beta, that is under root 30. And then sine phi is 0 from initial condition. So we have only sine 2 pi nu, sine 2 pi nu. And sine 2 pi nu, if you will put 1.125 into 360 degree, that will be 405 degree. So this will be the answer after one turn. So is it clear or not? Is it clear?
Yes, sir.
Just we have provided some initial condition. We have to use those initial conditions to find out the emittance. If we know the emittance, tune is given, beta is given, we can get displacement after one turn also. Now problem 9. Actually, one of the persons asked beam size of a divergent beam in a drift space increases linearly with length of the drift space. This is false. Actually, divergent beam in drift space doesn't increase linearly. How you can say it? Suppose a particle is going in a drift space with some initial x0 and initial x prime 0. L is the length of the drift space. So x will be x0 plus lx prime 0. It seems that, oh, this is linear in L, but it is not actually true for the complete beam. As we know, beam is ensemble of large number of particles. And here we are looking only single particle equation. So for large number of particles, the first thing which you can obtain the property is go for RMS values. So just obtain the RMS value, you will get the beam size. So under RMS of the x square will give the beam size, means spread. And when you will go RMS value for the RHS, you will get x naught square plus L square x naught prime square plus twice L x naught prime. And now you can see beam size doesn't increase linearly with L. It is some kind of higher order equations. In certain cases, when you have initial alpha 0, suppose you have initial alpha 0 means beam waist is there or maximum beam size is there, then this correlated term of x0 and x0 prime at that location will be 0. In that special case, your beam size will be just a simple expression of x0 square plus L square x0 prime. Okay, still it is not, you can say linear. It is parabolic kind. Now other problems. These problems were asked in the forum, so I covered those problems at first. Now I am going one by one on all the problems of this assignment. At some location, the value of this parameter alpha is minus 0.3. Downstream to this point beam will be. Alpha is minus and alpha is basically minus half d beta by ds. Means d beta by ds will become positive. D beta by ds positive means beta is increasing with s. Beta is increasing with s means beam size is represented by under root emittance beta, means beta is increasing, beam size is increasing, means it is a diverging beam. So minus in front of alpha or minus alpha is showing you diverging beam. The positive alpha shows you that converging beam. In a synchrotron, the magnetic strength Ks will always be a positive number, be a periodic quantity, both of these, none of these. K may be negative because if we have in one plane defocusing, then K will be negative in that plane. And for focusing, you can say positive. Or sign convention may be reverse also. So K may be positive, 0 and negative. So this option is not correct. Now periodic quantity. Definitely in synchrotron, suppose we have, this is the circumference of the synchrotron. Beam is going like this. Now after one turn, particle will see the same environment again and again. Means on each turn, particle will go through the same K. So K is periodic. K is always periodic in a synchrotron or storage ring. So definitely option B is correct. Now in a transport line, beam emittance is 200 nanometer rad. And at a location beta and alpha have the values of 50 centimeter and minus 1.2. What will be the beam size and divergence at this location? First of all, you have to convert all the quantities into the SI unit or in the same unit, you can say. So 200 nanometer rad means 200 into 10 raised to minus 9 meter rad, and 50 centimeter means 0.5 meter. Then you solve it. So beam size will be under root emittance beta. This will be in meter. And similarly for divergence, you need gamma. And beta and alpha both are given. So you can calculate gamma very easily because beam divergence is under root emittance gamma. So gamma you can calculate using this relation 1 plus alpha square by beta. Alpha is given minus 1.2 and beta is 0.5. So you can calculate the gamma also. And just putting the values of this gamma and emittance in here and you will get the beam divergence. So beam size and beam divergence. The correct answer is this. Normalized emittance of a proton beam is 9 millimeter millirad. What will be the unnormalized emittance of this beam at 10 MeV and 200 MeV? Actually, in course of LINAC, you were introduced with the adiabatic damping. Means as beam accelerates through the linac, its emittance becomes smaller and smaller. That is adiabatic damping. But normalized emittance remains constant. What is normalized emittance? Normalized emittance is just emittance multiplied by relativistic gamma factor. Don't be confused with twist parameter here. These are not twist parameters. These are relativistic parameters of the beam. So gamma and beta. Gamma is E by E0 and beta is V by C. So just multiply with emittance which we have studied so far. You will get the normalized emittance. This emittance remains constant throughout the acceleration. Now at a certain location in a synchrotron, beta function is 20 meter and dispersion is 0.8 meter. If beam emittance is 16 nanometer at, what will be the maximum displacement of a particle from the design orbit at this location if it has a momentum deviation of 0.5%? It is a very straightforward question. You have 0.5% delta P by P, means delta P by P is 0.5 by 100. Now just use this number in this equation. X is equal to root emittance beta. Emittance is given, beta is given. Just convert into the meter. 60 into 10 raised to minus 9 meter. Beta is already in meter, so you have into 20 plus D dispersion is also given 0.8 meter, and just use 0.5 into 100 here. So just plug the number and you will get the answer. If at a location twist parameter alpha is 0, then at this location beta may have. Now you know that alpha is equal to minus half d beta by ds. So d beta by ds will be 0. Means either beta has a maxima or minima at this location. So local maxima is also correct answer, local minima is also correct answer. So you have two correct answers here. Now in an optics, magnetic elements are arranged periodically, in which case periodic value of twist parameters cannot be found. Certainly if optics is greater than 2, you cannot have periodic solutions. If optics has trace greater than 2 means no bounded solution. You will get hyperbolic solution, and hyperbolic solution is not periodic solution. So for getting the bounded motion, you have to have trace less than 2. So option A is correct. If optics includes dipole magnet with gradient, no, this is not. Even in case of optics as a gradient in the dipole magnet, you can very well, it is just the dipole and quadrupole at the same place, you can consider it. In the case, you can get definitely periodic solutions. If initial condition or twist parameters chosen are not appropriate for periodic solution, we have discussed it 5 or 10 minutes earlier, that in a ring we have boundary value problem. If certain parameters are not fulfilling those boundary conditions, then you will not get correct solution or periodic solution. So this is C is also correct. If initial condition is not actually appropriate boundary condition, then you will not get periodic solution in that case. And it is always possible to find a periodic solution. No, it is not correct. We have seen that in case of A and C, you will not get the periodic solution. So A and C, these two options are correct. In an optics, if dispersion is non-zero, its value is affected by. Definitely dipole magnet also affects the dispersion, because dipole magnet itself generates the dispersion. So dipole magnet definitely affects the dispersion, and quadrupole magnet definitely affects the dispersion, because as the beam goes through the quadrupole magnet, it focuses. Focuses means dispersion becomes smaller after the focusing. So quadrupole magnets also affect the dispersion. In fact, quadrupole magnets are used to obtain the particular values of dispersion at certain location. Now there were some problem related to chromaticity, means why magnetic field which is required to correct the chromaticity should be even. We will see it. Suppose this is a dipole magnet and this is our design trajectory which is coming here, and after bending it is exiting from the dipole magnet here, and design momentum is just p0. Now let us suppose there's some another trajectory of the particle which is having some higher momentum, p0 plus delta p. Before entering into the magnet, these orbits were coinciding, means this particle was also traveling nicely on the design path. Now bending magnet separates its trajectory here. Similarly will be the case of p0 minus delta p, means lower momentum particle. Initially all the three particles were on the design trajectory, but as these particle passes through the dipole magnet separates the trajectories of these particles. Now we want to focus it because these are dispersed. So if we leave in this fashion only, these particles will go far and far from the design orbit, and at certain location it can hit the vacuum chamber. So we have to focus it. So definitely for focusing we need some quadrupole magnet. So this quadrupole magnet will send this p0 plus delta p towards this central axis like this. It will also send this p minus delta p trajectory also towards the central axis. However, because this has lower momentum, quadrupole exerts more force, means it has shorter focal length. So it crosses the design trajectory from here, while the higher momentum particle crosses the design trajectory from here. Means there are different focal points depending on the momentum. So we have spread in the focal length due to delta. This is known as chromaticity. Origin of the chromaticity is difference in focal length for different momenta in the quadrupole. Now chromaticity correction means this spread should become 0. So how it can be done? We will see it. So this is the spread. Now these are the dotted line on which particles were going after the passing through the quadrupole. Now if you want to make a point instead of this spread, what will you do? You need that this trajectory should go from here and this trajectory should also go from here. Means higher momentum particle have to bring somewhere lower, and this lower momentum particle should brought towards the higher side, and then these two will meet. How we can do this? So I enlarged this picture. Now you can see that this was the original dotted line of the higher momentum particle, and we need this thick line. So what kind of force should we apply? Definitely we will apply in this direction, downside. And for this lower momentum orbit, we also see from the picture that there is also a force required in this side. So Fx, and here it is F minus x, x is equal to 0 on the descent trajectory. So on axis, we need no force. If a particle is going on the axis, it should not be disturbed. But if we are on positive x side, we need a force on downside. And if we are on negative x side, we also, at this side also, we need force in the same direction. Means Fx should be equal to F minus X. This can be generated with the magnetic field, which is E1, means Bx should also be equal to B minus X, means field should be E1 for chromaticity correction. And definitely you will see that in sextupole magnet, which is used for chromaticity correction, field is E1. So I think all the doubts have been discussed here. If you have certain doubt is still left, then you can ask here in this forum.
Sir,
Yes.
sir, can you please go back to the
Which slide?
the eighth question? At certain location, in the cyclotron, the beta function.
At certain location.
Not this one.
This
sir,
one?
Next. No.
This one?
Next. No, sir. Next slide.
This
Yeah,
one.
this one. Yeah, this one, sir. I think the answer is 1.1 meter, not 5.1 meter. If you numerically solved it, it will come to 1.1.
Okay, I will check it.
Sure, sir.
Okay.
So this was the 10th question, right?
No, sir. Eighth.
No. This is the 8th question.
Oh, okay.
I will check the answer.
Sure, sir.
I have marked it on my slides.
Okay.
So no, Dhanush has dot in the 10th problem. So is the dot no solved or?
No, it's not 10th problem. I said 8th one.
Oh, okay. I have misheard it. Okay. So this was your dot. Like the answer was okay. Maybe. Okay, sir. Thank you for uh, for the detailed solution. I'll also upload the slides that you have sent.
I already shared.
Yeah. I got it, sir. So, Dhanush, do you have to ask anything else?
No, nothing.
Okay. Okay, sir. If it, then we can meet next Saturday, and Pitambar sir will also be ready to share his slide. So,
Okay, bye to all.
okay. Thank you. Bye.
Thank you, sir.